I'm now going to explain why integration with respect to arc length does not depend on the parameterization of the curve, assuming that the parameterization does not backtrack. Informally speaking, we're only covering the curve with one coat of paint. So here's a picture. We have a parameterizing interval, say from A to B, and let's call the parameter t. And this is being mapped by some function r to a curve in the xy plane. I don't know exactly what this curve looks like. Maybe it looks like this. So here's r of A and r of B. Now I want to choose a different parameterization of the curve by a new parameter. Let's call it u. Let's say going from C to D. So t is going to be a function of u. Say t equals g of u. There are now two ways to think of this curve. I can think of it as t mapping to r of t, or I can think of it as u mapping to r of g of u, or I'll write this as t of u. And I want to show that the integrals with respect to arc length, as defined using these two different parameterizations, are the same. Now, I need to make some assumption here. I need to assume that my reparameterization is not going to introduce some backtracking. So the formal way to say this is I'm going to assume that G is a bijection. And also I want it to be differentiable. So integrals with respect to arc length need the parameterization to be differentiable, otherwise the definition of the integral doesn't make sense. So there are now two cases. The first case is where g of c is equal to a and g of d is equal to b, and since there's no backtracking, we also need that the derivative of g prime, is always greater than or equal to 0. Okay, now the integral with respect to arc length, as computed using the u parameterization, looks like this. So it's the integral from c to d of f of r of t of u times the length of the velocity vector, which is d du of r of t of u du. And I want to simplify this to see that it's the same as the usual formula for integration with respect to arc length. Now, so this is integral from c to d of f of r of t of u. And this d du of r of t of u, by the chain rule, I can write this as d by dt of r of t times dt du. Okay, so here d by dt of r of t is a vector. So this is the velocity vector of the curve r with respect to t. And dt by du is a scalar. This is the same thing as g prime of u, and in particular, this is a non-negative scalar. Now, remember that when you calculate the length of a vector, if you multiply a vector by a scalar, that multiplies its length by the absolute value of that scalar. So I can pull this scalar out here to write this as the integral from c to d of f of r of t of u times d dt of r of t. And because it's non-negative, I don't need an absolute value on it, so it's just dt du du. And now, informally speaking, we can cancel out the du's here, so we can recognize this integral is what you would get by a substitution of the variable u, and I can rewrite this as a t integral. So now, instead of u going from c to d, t goes from a to b, of f of r of t times the length of r prime of t dt. So now this is the formula for the integral with respect to arc length using the t parameterization, and this is the formula using the u parameterization, and I've shown that they're equal. That's what I wanted to show. Now, that was just the first case. So the second case, let's draw this in green. This is where g of c equals b and g of d equals a, and now g prime is going to be less than or equal to 0 everywhere. So this is where the map from u to t is switching direction. Okay, so what happens here? Well, now the scalar dt by du is non-positive. So I need a minus sign here when I pull the scalar out. And also, because g of c is b, I have to change the limits here. So now instead of a b here, I have an a. Instead of an a here, I have a b. And I still have that minus sign. And now I can switch the limits of integration and cancel out the minus sign. So this becomes the integral from a to b with no minus sign of what we had before. So it still works. Okay, so in conclusion, there are two cases. In the first case, the map from u to t does not switch direction, and it all works. In the second case, it does switch direction, and we get two minus signs. We get one minus sign because dt by du is negative, or non-positive, and we get a second minus sign when we switch the limits of integration, and those two minus signs cancel out, so it still works.